For this project, we are examining a nuclear fuel refinery plant, and our goal is to maximize our on-site storage mass of these nuclear fuel materials. So for a little bit of background on this project, we saw an increase in alternative energy demand, and particularly there is a renewed interest in nuclear energy. Because of this, there is an increased demand in nuclear fuel. In the process of refining nuclear fuel, there are two inputs. The inputs are uranium ore and hydrogen fluoride, and the output, which is essentially nuclear fuel, is the refined uranium hexafluoride, which will be sent to a nuclear power plant for further energy production. To specifically put our problem in the context of optimization, we want to maximize the sum mass of our hydrogen fluoride and our refined uranium hexafluoride.
We are using the American Industrial Hygiene Association Emergency Response Planning Guidelines, or ERPG, as a basis for our constraints. We will be using ERPG Level 3 concentrations for our maximum allowable concentrations in this problem, which are 41.08 milligrams per cubic meter of hydrogen fluoride and 30 milligrams per cubic meter for uranium hexafluoride. Here we have the Pascal-Gifford Puff model, or PGP. This defines the concentration of a chemical, taking into account the height, defined as z, the distribution of the chemical, defined as y, and the wind speed, defined as x. For this problem, we assume the worst-case scenario, which the EPA defines as all chemicals being at or near ground level, a stable atmosphere, which minimizes chemical distribution, and a minimal wind speed, which the EPA defines as 1.5 meters per second. Taking into account that we are using the worst-case scenario, we see that we can simplify our equation further. Above you see the original PGP model, and below the PGP model taking into account that our z and y variables are both 0. This will be the equation we use moving forward.
In order to clearly identify mathematically the components that will be used, we will label hydrogen fluoride as component 1 with the subscript of 1, uranium hexafluoride as component 2 with the subscript of 2. X is going to be the distance from the source of initial mass or the holding tanks. We will be doing this relative to a 5-mile dispersion radius. This implies that the center of mass of the holding tank is always going to be 5 miles away in the x, y, and z direction. Based on our constraints, we will not have the y or the z dimension. So when we look at our equation, our simplified equation from the PGP model, our Qm is equal to the mass, which is going to be equal to our EPRG3 value of the specific component multiplied by the denominator. The denominator is a function of how each species present in the atmosphere is going to disperse. So if we were to take our EPRG3, which will be a mass per volume, times the volume of dispersion, we will get a mass. Mathematically, we will take the left-hand side, which is our Qm, or our x1, minus the right-hand side. We will set that equal to 0. This is basically a mass balance on our 5-mile volume space that we had defined previously.
To solve this problem, we used the fminCon function in MATLAB, where our decision variables are x1 and x2, x1 being the mass of hydrogen fluoride and x2 being the mass of uranium hexafluoride. Our zeta is negative x1 minus x2 because MATLAB defaults to minimization. We have a bunch of constants defined, sy1, sx1, sc1, sy2, sx2, and sc2. And we have the conversions between parts per million to milligrams per meters cubed. Our nonlinear constraints are C1 and C2. These are the mass balances between the initial mass and the dispersed mass, just as Robert mentioned. Our final solution is X1, or hydrogen fluoride, is 700 grams. X2, or uranium hexafluoride, is 511 grams. And our zeta star is 1,211 grams.